So we were talking about implementing an array-based list. And we reached this point here where we want to implement an iterator for our list. So the way this is going to work, it's going to work similarly to the way the iterator worked for our range class, right? So remember when we wrote a little range class so that you could emulate a Python-style loop? Our iterator for range was basically just a counter. So the same is true for a list, right? Because to iterate over an array-based list, you just want something that moves from index to index to index. So like the range class, we're going to have an inner nested class that implements the iterator. Right? Now remember this iterator, hang on just a second here. Okay, so remember this inner nested class. It has access to the fields of the class that it's defined inside of. So our array iterator class has access to the fields of our list class, right? So it can find the size of the list and get it can go into the array that the list has. It implements the iterator interface. And so just remember what an iterator is, right? It's an object that knows how to iterate over a collection of elements or over a sequence of values. And also recall what the iterator interface looks like, right? It has a hasNext method, returns true if there's another value to iterate over in the sequence. Next gives you the next value in the sequence, right? And we didn't look at this method before. Right? So when we implemented range, we didn't bother with remove because it doesn't make sense to remove a value from a range. But for a list, you may want to remove an element from the list while you're iterating over it with an iterator. So the iterator interface defines a default method that just throws an exception, right? So in other words, if you don't override the method and you try to call remove, or someone tries to call remove, you just get an exception, and it says you can't remove an object using this iterator. Right. Okay, so what does remove do if you have an iterator? So remove removes the element that was most recently returned by next. Right? So remember how this iterator thing works, right? You make an iterator, you call next, you get the first element in the sequence. You call next again, you get the second element, and so on and so on and so forth. Right? So if you call next, you are allowed to call remove. Right? So you call next. If you decide you want to remove the element that was just returned by the iterator, you can call remove. And that will remove the element from the collection that was just returned by next. Right? So if you call next and then remove again, that doesn't work because remove removes the element that was most recently returned by next. Right? So you can't remove an element. You can't. Every time you call next, you're allowed to remove exactly once. So our iterator needs to know, has it called or has remove been called once? Has remove been called if next has been called once already, right? And if it hasn't, then it throws an exception. So we need some mechanism to remember, has next been called, and can I call remove? So using an iterator is it's the only safe way to what's called filter a collection. So when you filter a collection, that's when you iterate over a collection and you remove values as you're iterating over it. Right. So for example, you might want to remove all the negative elements from a list or a set of integers. Right. And the way you do this with an iterator is as follows. So you write a little loop. Right. You make an iterator as your loop variable. So that starts at the start of the set or sequence or list. Sorry. Your loop termination condition is just has next. So the loop runs as long as the iterator has some other element to look at in the sequence. Right? And there's no update statement. Right? Instead, you're going to advance the iterator inside the loop. Right? So iter next returns the next element in the sequence and then advances the iterator one position. Right? Once you have the value from the iterator, you can check, is it less than 0 in this case? Right? And if it is, now we can remove the element from the sequence using the iterator. Right? So you can, if you're very careful, you can write another type of loop that doesn't use an iterator. at least for a list anyway, that does remove the element from the list. So you can do it without using an iterator, but you have to be extremely careful how you do it. And you also have to know what type of list are you removing from. Right? But using an iterator always works. Okay, so how is this thing going to, how are you actually going to implement this thing? So an iterator is for a list is sort of like a cursor for a text editor. Right? So notice my little blinking cursor right here. Right? That cursor sits between two letters. Right? The letter in front of it's the Y, the letter after it is the I. Right? So previous letter and the next letter. So an iterator sits between elements in a list. Right? So my iterator is shown in red. Right? The previous, the element in front, I guess before, the element before the iterator is the 13, and the element after the iterator is the 6, right? And the indexes of those two elements are 7 and 8, right? And so if your iterator is in this position, the only way it could have got to this position, because it starts at the front, is if you called next a bunch of times. So when the iterator reaches this position, the element that was most recently returned by next was the 13. Right? The element that will be returned by the next call to next will be 6. Right? And so what we're going to do is we're going to store the index of the next element in the sequence and the previous element in the sequence. Right? And our iterator sits between those two values. Okay, so if you call next, then the iterator advances one position to the right. Right? So it's now between the elements at indexes 8 and 9. Right? If you ask the iterator for the value, it returns the 6. Right? And similarly in this picture here, if you ask that iterator for its value, it would return the 13. When you get to the end of the list, so this list has 15 elements in it, right? There's room for 16 of them, but it only has 15 elements in it. So when you get to the end of the sequence or the list, right, has next will return false, right? So in other words, there are no more elements in this sequence, right? If you try to call next with this iterator, you get an exception because there is no next element. And when you make a brand new iterator that starts at the beginning of the sequence, right, over here, right, next will be 0, and previous, in this case, there is no previous element, so we're going to use -1 to indicate that the iterator is at the front or at the start of the collection. We're going to use -1 for something else as well, so hang on for that. Okay, so here's our class. There's array iterator. It's going to have a field called next, right? And it has a field called previous. Right? So next is the index of the element returned by the next call to next. Right? And previous is the index of the element returned by the most recent call to next. Right? If we remove an element from the collection using remove, we're going to change previous to -1. And that's going to be the way that we can find out, is there an element that we can remove using this iterator? So our constructor starts the iterator at the front of the collection, so it starts it here. Right? So next is going to be 0, and previous will be -1. Right? So remember, these are indexes. Okay, so how does has next work? So if you go back to the picture here, right? Oops, sorry. All right, so this iterator is at the end of its collection. Right? Has next should return false in this case. Right? So if you look at that iterator, its next value will be 15. Right? And so that 15, right, is equal to the size, will be 15, right? So that 15 is equal to the size of the list. Right? There's 15 elements in this list. Right? So when next is equal to the size of the list, you know that there are no more elements. Right? So has next returns true as long as next is less than the size of the list. Right? Now remember, the size of the list is stored in the ArrayList object. Right? So to ask the ArrayList object for its size, right, you have to use this funny syntax, right? So sArrayList dot this dot size, right? sArrayList is the class that the iterator is defined inside of, right? Because it's a nested inner class, there is an ArrayList object of some kind that owns that iterator, right? And so the object that owns that iterator, you can access its fields using this syntax here. It's a very awkward and ugly syntax. I'm not sure why they chose this, but that's the way it is. Okay, so what about next? So in the simplest case, next just returns the element at this dot next, right? So that's easy, right? I just go in, I just ask the list, right? What is this next, right? So I can use get in this case if I wanted to, right? Now because you have access to the fields of the list, it's slightly more efficient to go right into the array, right? So sArrayList dot this dot arr, that gives you the array that belongs to the array list. Right? And now I can just use this dot next because that's the index of the next element. Right? That's slightly more efficient because get validates the index. Right? So you avoid the if statement that checks whether or not this dot next is valid. Right? Okay, so once you've gotten the next element, you're going to return it. So we're going to return that at the end. Right? But you also have to advance the iterator one position. Right? So you move next up by 1. Right? But you don't move previous up by 1. Right? And we'll see why in just a second. Instead, you're going to write this previous equals this dot next. Right? So that advances the value of previous correctly. Right? Now the reason we're not going to do that, well, we'll see why we don't do this in just a second. Right? So get the element, advance the iterator, and then return the element. Right? Now this method is supposed to throw an exception if there is no element, if there is no next element. Right? So just call hasNext to determine if there is a next element, right? And if there isn't, throw no such element exception. So that's the standard exception that you're supposed to throw for an iterator when there is no next element. All right, so how about remove? So here's an iterator sitting between indexes 8 and 9, right? The most recent element returned by the iterator was the one at index 8, right? So the 6. So if we remove that element, right? Sorry, let's back up one step. So if I have this iterator, I know that the next element that should be returned by the iterator is the 10, right? Now what happens if we call remove, right? Okay, so calling remove on that iterator, right, is supposed to remove the 6. Right? So in other words, I need to remove that element there. Right? Now this is an array-based list, so to remove that element, we're going to shuffle all of the following elements over one position to the left. Right? Okay, so what happens to this iterator now? Right? So I'm going to remove the 6, right? So 10, 4, 14, 5, 1, 11, they all move over one position to the left. So there they go. Right? Now, that iterator, its next index was 9, right? So that's not right anymore, because if we call next on that iterator, we're going to get back the 4 and not the 10. So that's not right. Right? So next is now at the wrong index. Right? But that's easy to fix. Right? You just take next and subtract 1. So in other words, we move next one position to the left, like that. Right? So now our iterator, you can imagine that shuffles over one position to the left. Right? So now, given that iterator, if I call next, I'll get the 10. Right? But what about removing the element? Right? So if I remove the element from that iterator, right, it's supposed to, so number one, you're not allowed to remove the element. Right? So you just called remove, right? And you called next, then you called remove. You're not allowed to call remove a second time. Right? You have to call next again before you can call remove. So somehow I need a way to know we've removed an element. Right? And the easiest way to do that is to take previous and set it to some invalid value. Right? So in other words, set previous to -1. Right? And that indicates that you can't call remove again without calling next. Okay, so if previous is equal to -1, right, then we know that we haven't called next yet before calling remove, so we throw an exception, That's the standard exception you're supposed to throw in this case. Okay, so if previous is not -1, then you know you can remove the previous element. Right? And so the way you do that is you use the list method remove. Right? So you ask the array list to remove the element at that index. Right? And that causes all the elements to shuffle over one position to the left. Right? Now you can decrement next. Right? And then update previous to indicate that an element has been removed. Right? And now your iterator class is complete. Right? And that also completes our array list class for the time being. Right? So there's the iterator for an array-based list. Any questions on how this works? It's really just a bunch of bookkeeping, but you have to be a little bit careful about how you do things, right? The tricky part in this implementation is that line right there. Right? So if you write this previous minus minus, or this previous equals this previous -1, right? That doesn't do the correct thing if someone had called remove, right? Because if someone calls remove, the previous gets set to -1, right? And so if you just add 1 to previous, you end up at 0 instead of being at next -1. Okay, moving right along. So that wraps up the array-based list. So now we're going to look at how you implement a singly linked list. Right? And so a singly linked list is basically a lot like, it's going to be a lot like a queue or a stack of linked nodes. Right? So in a linked list, you've got the head node at the front, so that's called the head node. Right? And you've got a node at the end of the list, so that's the tail node. You don't always keep track of the tail node. Right? So in the simplest linked list implementation, all you have is the first node of the list. Right? So you only have the head node. So in a singly linked list, each node has a link to the next node in the sequence. In a doubly linked list, each node has a link to the next node and the previous node. Right? And so that's a singly linked list, right? Which looks a lot like a stack or a queue. Right? That's a list of length 3, so you've got a head node and you've got a tail node. Right? The empty list, your head node is null and your tail node is null, so there is no head or tail node. And the structure of a linked list, you can think of it as is structurally recursive. Right? Just like a stack is structurally recursive. Right? So for example, the head node, the first node is the head node of a list of length 4. Do I have a picture here? Oh, I do. Okay. So the second node is the head node of a list of length 3. Right? The third node is just the head node of a list of length 2, and the tail node is just the head node of a list of length 1. This makes implementing sublist for a linked list quite easy to do. Right, so remember how sublist works for a list? Right, so sublist for a list gives you back the part of the list corresponding to some subsequence of the list. Right? So if I wanted the sublist starting at index 1 and I have a linked list, right, that's dead easy. You just make a linked list and you set the head node to that node there. Right, and away you go. So it's really easy to do with a linked list. Okay, so because the structure of a linked list is recursive, just like with a stack, you can write linked list algorithms recursively. Right? So if you wanted to compute the size of a linked list, that's easy to do. Right? So to compute the size of a linked list, I can do it recursively, so I'm going to call a recursive helper method. Right? My recursive helper method takes in a node. Right? The node is just the head node of some linked list. Right? So you start by passing in the head node of the actual list. Right? If the head node is null, then you know the size of that list is 0. Right? If it's not null, then there's at least one node in that list. Right? So the size of that list is 1 plus the size of the rest of the list. Right? How do I get the size of the rest of the list? I just recursively call recursive size, passing in the node that corresponds to the head node of the rest of the list, right? But that's just head.next. Oops, sorry. All right, so that takes us to the next set of lectures. Oops. Where did that go? That exam date's for obviously 2021, so that's not right. Okay, so we're going to create a class that implements our simple list interface. Right? This time it's a linked list, so it's called sLinkList. Right? It's going to have the same generic node class that we used in the linked queue. Right? I guess here we're going to, so our implementation here is going to be slightly different. So I'm going to make node package private this time. Right? So in the previous implementations, it was private. So no other class can access them. I'm going to make them package private so that we can create some other classes that can go into a linked list and get its node and access the node class directly. Right? Okay, so here's our static node. So there's our node class. It's the same as before, so it's empty right here, right? But it's the exact same as before. Right? We're going to keep the size of the length of the list, so the number of elements in the list. We're going to keep a reference to the head node. We're going to keep a reference to the tail node. Not all implementations keep a reference to the tail node, right? But you always have a reference to the head node. Okay, we've got a package private method head that returns the head node, and we've got a package private method tail that returns the tail node. So that's going to let other classes in the same package get to the nodes of a linked list. All right, what does an empty linked list look like? So its size is 0, right? Has no head node or tail node, right? So they're both null. Size is easy, as it is for all of our data structures so far, right? You just return this dot size because we're keeping track of the size. Right? To add to the end of a list, it's exactly like enqueuing to the end of a queue, right? So it's exactly identical. Like with the queue, so in our particular linked list implementation, if you try to add to an empty list, there is a special case when your list is empty, right? So remember, we're keeping track of both the head and the tail node. So when you add to an empty list, both that field and that field need to be updated, right? Normally, you only need to update the tail node, right? Because you always add to the end, right? But if there is no head node, you also have to update the head node. Right? So when you add to an empty list, both head and tail get updated so that they refer to the node that you just created. Right? Otherwise, right, when you add to the end of a non-empty list, that just involves modifying the tail. Right? So if I want to add to this list here, right, you make a new node. Right? You hook the tail up to the new node, like that. Right? Update the size of the list, and away you go. Right? And then finally, update tail so that it now points to the newly added node. Right? So it's easy. Right? If the size of the list is 0, right, update the head node. Right? Then set the tail node so that it points at the new node n. Right? Increase the size of the list by 1. If the size of the list is not 0, then update, make the node. Right? Then update the tail so that its next link points at the new node, right? Sorry, that is bugging me. There. Right, so make the node, update tail.next in the usual case, right? Then update this dot tail, and then increase the size of the list by 1. Okay, so getting and setting by index. So in a linked list, this operation is slow, right? So if you ever need a list and you are getting or setting values by index, or removing by index, or inserting by an index, right? All of these operations are going to be very slow for a linked list, right? Because linked lists don't have random access to the nodes, right? To get to any particular node in a linked list, you've got to follow the sequence of nodes, right? And you have to do this for every method that operates by index, right? And so it's really useful if you write a method that can both validate an index, but that's easy to do, right? And then move to a node at a specified index, right? So validate's dead easy, right? You just check if the index is less than 0 or greater than or equal to the size. Throw an exception if it is, right? Moving to a node, though, this involves following a sequence of links, right? Okay, so if I want to move to a node, what you have to remember is you always start at the head node, right? So if I want to go to the middle of a list, I have to follow roughly n over 2 links in the list, right? So you just use the little general iteration pattern that I showed you previously, right? You start at some node, so in this case the head, right? I want to move to that index, so I write a little loop, right? That runs index number of times, right? And now you just advance the node that many times, right? So n equals n dot next, right? So that's the general way that you advance the node, right? You have a special case up here, right? So if you want to move to the end of the list, you can remember that you already have that node, right? That's just this dot tail. So if the index is equal to the size minus 1, you don't have to move anywhere. You can just go straight to the end, right? And so that's useful. So that's one of the reasons why it's useful to keep track of that tail node. And then finally, you can return that node n, right? So here's a little package private method that moves to a specified, moves to a node at a specified index, right? And we're going to be using this over and over and over again. If you want to do this recursively, you can, right? So there's move to again. And for this method here, we're going to implement it recursively. So we'll call the recursive version of the method, right? The recursive version of the method starts at this node n, right? And moves that many locations relative to n, right? So if you move 0 locations relative to n, you're at n. So you just return n, right? Otherwise, you move to the next node. So you update n to be n dot next, right? And then move index minus 1 locations relative to the next node, right? And that will also move you to the next node. Okay, so once you have get and set, once you have move to, right? Get and set are now trivial to implement, right? So if you want to get the value of a node by index, get the value of the list by an index, right? You just call move to the node, and then look at the element that's in the node. Right? So notice that move to, because it has to follow all the links in the sequence, right? Its worst case complexity is always on. So get, validate the index, move to the node at that index, return the element in that node. Right? If you don't have move to, you end up writing that loop over and over and over again. So it's really useful to have this method. Okay, so what about set? So for set, you validate the index, move to the node that you want to update. Right? Remember what's currently in the what the element is in that node for now, because I'm going to return it later, right? And then update the element to the new element. Okay, so unlike an array-based list, though, so linked lists do have some advantages, right? One of the big advantages is that if you want to do something at the front of the list, it's very fast, right? So inserting an element at the front of the list is just like pushing an element onto the top of a stack, right? And so that has complexity O1, right? Whereas in an array-based list, if you want to insert at the front of the list, that has complexity On, right? Because you have to move all the elements over one position, and then you can set the element at the first position. Right? Okay, so to add to the front of the list, right? So I want to add the element to the list of length 4. You make a new node, right, which I'm going to call toAdd, right? And then all you do is join that new node to the front of the list, right, or to the head of the list. Right, so make your node, right? Hook it up to the current head of the list, right? And then update the head of the list so that it's now the new node, right? And then increase the size of the list. There's a bug here. Anybody see the bug? Well, there's something missing. The code here is correct, but there's something missing. So when you, yep. Head.next. So let's see. So we make our node. We set its next reference to point to the head. So that's what we did right there. Right? Then you update the head so that it points at the new node. Right? So now the head points at this node here. So head.next is already set. Yep. But there's a special case missing. Yeah. That's right. Yeah. So just like with add, if the list is empty, you have to update the back node too. Right? So somewhere in here, right? Probably here after either. So you have to, it depends on whether you update before or after you update the size. Right? So before you update the size, if the list is empty, you have to set this dot back to equal to add. If you do it after you update the size, then you have to check if the size list is 1. Right? Now update this dot back so that it points to add. Right? But yes, there is a special case missing here. Okay, so this one's a little bit more complicated, although I think you know how to do this already. So to insert into the middle of the list, you have to fiddle around with a bunch of links. So there's a bunch of bookkeeping involved when you insert into the middle, because you have to update possibly several nodes. So we'll look at that next time, because it's already 17 after the hour. And we'll complete the linked list implementation in the next lecture. I think we're going to do an iterator for this too. Although I think that'll be in the next set of slides. Sorry?
Are there slides 33 and 34?
Not on OnQ. Yeah. Oh, there is an iterator. Yep.